And this is of thermodynamics that was contributed by Gibbs in the 1870s. And I hope that it might elucidate something about these questions about the equation of state. So, in order to see what the problem is, and we know this is just a particular specific system. Not all thermodynamical systems need to be ideal gas. They're characterized by peculiar equations which hold for those systems only. The gas law temperature and volume. Now, you might think, okay, this is the ideal gas law. This is the definition of an ideal gas. In fact, there are many textbooks that will tell you so. Answer is wrong. There's yet another property of the ideal gas. You've got to say something about how the internal energy, even if you take it also as a function of volume and temperature, actually does not depend on the volume, or some people go even further, that actually it's not only independent of volume, it's only linearly dependent on temperature. That is to say, where now is constant. In the literature, this an ideal gas and this a perfect gas. About half of the literature does it the other way around. There's no unanimity whatsoever. The distinction between them does become important when you want to talk about third law of thermodynamics, but otherwise not much depends on them. However, you might say, could I derive any of this from the ideal gas law? The answer is no. This is a completely independent piece of information. And it was only established by doing extra experiments, the Joule-Kelvin experiment in this case, on gases to see whether it was actually true. It doesn't follow from Boyle, Gay, Cirque. So, now we have two equations for this decentralized variation that we need to characterize an ideal gas. That's a bit embarrassing. So now what people sometimes do is, this is called the thermodynamic equation of state. And this, for some reason or other, sometimes called the caloric equation of state. And this situation extends to more systems. Some systems might have three equations of states. Some states might have more. And it's, in general, very hard, if I don't have any systematic manner to proceed, to find out how many equations you need to actually characterize a thermodynamic system. And this is partly due to the fact that I've never made any systematic choice about what variables I should choose. So here comes Gibbs. And he points out, he's a much more sophisticated mathematician than his colleagues. And he points out that if you take, for example, this equation, as David yesterday also reminded us, if you take this equation and you would give us energy as a function of volume and energy, so suppose I know
just say the last thing you said. I give energy as a function of
entropy and volume, right? So I use the symbols that appear in the differentials. And I compare that with the chain law of differentiation. You can simply read out that the temperature must be the partial differentiation of energy with respect to entropy, and pressure would be given by differentiating energy towards volume.
You need minus sign.
With a minus sign. And if I wanted to know other quantities like a specific heat, we have to differentiate once more sometimes. But the general point is, if you were to know this function, then you can determine all the other relationships by differentiation. So now you would need to have only one function, and it would contain all the information about the system in that single function. Whereas here you would need to use as many independent equations as, well, I don't know how many you need. In the case of ideal gas we need 2, but in other systems we might need more. In this case we can concentrate all the information we need about the thermodynamic system into one function. So that's why Gibbs called this the fundamental equation. Now, unfortunately, entropy and volume are not the easiest variables to work with because, for example, entropy is hard to measure. But you can do the same thing, of course, for, and if I, just bring this to the other side, divide everything by T, I can also express entropy as a function of energy and volume. And now the same thing will work. This too will give you a fundamental equation that contains all the information about the thermodynamic system. Unlike the equations of state that were used traditionally. Now, you might still think, well, but actually, for me, energy and volume are not the most transparent variables to use. I would very much temperature, because I'm used to that as independent variables. Well, you can still do that, but as Gibbs shows, what you would need to do then is to introduce other functions defined by Legendre transformations, which would allow you to contain all the information into a single function. So, for example, you define the free energy if I'm correct. Minus. And then the free energy, and so you can simply see if you do that, then some of these differentials will drop out, and in fact, entropy and temperature will change their roles. So this is a function that can be expressed in terms of volume and temperature. And then it would also give you a fundamental equation. And then there are variations. There's the enthalpy, and there's the Gibbs free energy, and there are all these types of thermodynamical potentials, each of which would play a similar role in that, is to say that if you would use that potential in terms of a particular choice of variables, it will give you all the information that's possibly needed. So, there's at least one part of this black magic box that David presented yesterday that we can say something more about why it works, and what alternatives we could have to make it work just as well. Okay, but this is still classical thermodynamics. Of course, the recipe how to calculate those things from a specific microscopic model, that is not part of classical thermodynamics. Well, this was just a side remark. I want to be talking about Boltzmann and Gibbs. And in order to do that in a sort of systematic fashion, I want to be talking about two theories, so-called kinetic theory of gases and statistical mechanics. We try to put them side by side. And before I get even to that, and take a short detour in history, what we're going to do, of course, is going to consider the microscopic constitution of particular systems, in this case a gas. How should we picture that? And speculations about that were, of course, also as old as physics is. In fact, for example, Boyle had his own model of a gas. Boyle was the famous author of Boyle's law, so he knew that if you compress the gas, air in this case, its pressure rises. It tries to resist compression. How is that, and why does that happen? Well, Boyle thought that gas is composed of little particles, and those little particles are stringy, woolly, or feathery substances that take up a lot of space. And if you compress the gas, you are deforming those little particles. In other words, for Boyle, compressing a gas is like compressing a pillow. You can squeeze down its volume, and then when you let it expand again, it will take its original shape. That's how he pictured so all the gas theories. Newton, of course, was also one who was known to engage eagerly in speculations and hypothesizing. And so he had a model of a gas too that could explain why it resists compression. And the idea was simply that it consisted of small particles that, however, exert opposing forces to each other, repel each other quite strongly. And so if you try to compress it, you try to bring those particles closer together, then you need a force to do that. And if you let it expand once again, they move apart. So, strong repelling forces. Now, all of those theories, and there were, of course, many other models you can possibly think of. What is striking about all of those is that they're completely static. Motion plays no role whatsoever. And so, the first theory that said that the pressure of the gas and maybe its temperature actually has to do with motion of the constituting particles. That was due to Bernoulli, that is Daniel Bernoulli. And this is from 1732. And he had a picture of a gas in which there are tiny particles that move about in free space, and they are flying in all kinds of directions. And they exert pressure on the wall simply by bouncing off it. And if you compress the gas, you will see that you have to exert a force simply because, and force rises simply because more and more particles start to bounce on the wall. In fact, Bernoulli not only knew Boyle's law, but he knew the full ideal gas law. And he also said that temperature would be proportional to the square of the velocity.
You know, so I've never read Bernoulli. Does he give reasons for why, you know, the Newtonian picture or the Boyle picture seems so natural? What, you know?
Well,
does he say why he wanted? Presumably he's got reasons.
It seems natural, but of course one of the things that they would have problems with is the fact that a gas simply fills every volume you allow it to fill. If there's no motion whatsoever, how come that a gas will occupy so easily?
Well, Newton's model will do that.
Yes.
Right. And when Bernoulli's writing, Newton is almost godlike in authority. Right.
Yeah, I don't know. I've read a little bit about Bernoulli's. I mean, it's a small fragment in a large book on hydrodynamics. But I don't know whether he just presented his model as, look, here's an alternative way of looking at things, or whether he said, you know, apart from that, I have devastating arguments against Newton's theory. I don't know whether he... I don't think that the latter was the case. But this is generally seen as the rise of kinetic theory of gases. And you understand now why it has this name. We could, of course, there are two essential assumptions in the theory. namely that gases are actually consistent of small particles. So it's a molecular theory, but since molecular theories were already well known, the additional point that it is a theory about the motion of the particles is the one that gave it its name in order to distinguish it. But that's not to say that the molecular part is unimportant. Now, Bernoulli got surprisingly far and a surprisingly modern point of view. And there were, in fact, a couple of good things. So, for example, they already predicted that if you would increase the density of the gas very highly, you should expect deviations from the height of gas law. Because these particles are not point particles. They have their own volume. There are also many things that Bernoulli didn't have. So, for one thing, he never assumed that the particles collide among each other. They only collide with the wall. The other thing is that he assumes that although their direction of motion is somewhat at random, they all move with the same velocity. He has no averages over velocities. In fact, he has no probability considerations or statistical considerations at all. And I think actually that's quite, I mean, from a modern perspective, that seems obviously, this sort of cries out for a statistical consideration. But in Bernoulli's time, that was not a very natural thing to do. Probability theory was rather young. In fact, it had been developed by Daniel's uncle, Jacob. Daniel knew all about it. He was himself one of the best theoreticians in probability alive in Europe at that time. But in that early classical conception of probability, probability was just a measure of certainty. It was something that we ascribed to, for which we use to measure our belief in things. But it was not something yet that could also be regarded as an empirical statement about how large populations of things behave. So the frequency interpretation of probability was not current yet. And if you don't have any frequency interpretation of probability, it seems a very odd thing to do to try and express your degrees of belief about a particular gas system and think that in doing that you would learn something about its physical behavior. So although Bernoulli at that time had the best knowledge of probability you could think of, and he had one of the best models of gas theory you could think of, both in the hands of the same author, he never thought that there could be a relation between these two areas of his own expertise. Now, unfortunately, or maybe part of the end result of what I've just been trying to say, after Bernoulli had presented his model, this was not just a happy start on its way to full application and further development and a blossoming new theory of physics. In fact, after this, it was completely forgotten. It lay dormant for more than a century, and nobody worked on the theory at all. And as I said, I think people still lacked the conceptual tools that would help them to bring the theory to further application. And if you don't have statistical ingredients in the theory, the only way you could say more about the system would be by actually trying to solve the equations of motion, which is a formidable task that nobody ever attempted. And that's why, I guess, you couldn't say more about the model, much more than Bernoulli had already said. It just emptied the cup.
Another question?
Yeah.
So, am I right in thinking you said a moment ago that he took the velocities of the particles to be the same?
Yes.
So then, how did he make sense of things like, you know, if I start to push on one side of a cylinder containing this, then at that point, does the velocity of all of the particles increase at once?
No. When I said they move at the same speed, I'm talking about an equilibrium situation. If you start to move things like a piston,
Right.
then of course you're not in equilibrium, and of course the idea is, although I don't think he actually explicitly discussed this, but of course the idea would be that the particles that hit the piston would receive a higher kickback, and that somehow perhaps this extra kinetic energy will spread among the other particles as they also hit the piston. It's not, because there's no mechanism for of spreading kinetic energy, distributing kinetic energy amongst the particles, since they don't collide. All the redistribution would have to come through the collisions with the wall. And as long as the wall are static, then given the fact that the particles have tiny mass, then the absolute value of the velocity before and after the collision will be the same. So they don't gain any kinetic energy from the wall. But if the walls are moving, then of course they would. But it would take some time for that to re-establish the uniformity of the velocity. And I also don't think that Bernoulli made a great point of this. I'm not trying to suggest that for Bernoulli it's an important assumption in the theory that all these particles have the same velocity. I'm just trying to say that he assumed they had the same velocity, probably out of simplicity, or maybe because he hadn't considered the matter any further. He certainly writes as if they all have the same velocity. But I'm not trying to suggest that it was an important and fundamental assumption for him.
Yeah, I was going to say that. I don't think he actually commits themselves to saying they have all the same velocity, but that's the calculation he does.
Yes.
He does a simple case as if they all have all velocity, but I mean, I don't know. We've all done that. Like the first time you start thinking about the kinetic theory of gases and you want to know a relationship for pressure and velocity, you write down things that all involve one velocity and do that, right?
Yeah, it's a calculation that gets at the
It's the easiest calculation to do, right?
No. So anyway, Stefan Brush has written a wonderful history book on the history of the theory. In any case, there's a slow reappearance of the theory in the mid-19th century, in particular also due to Clausius and others, and they shortly start to present more useful results. They also give some estimations about the speed of the particles that they would have in order to accommodate the usual observations about gases at room temperature, and it's in the order of 1,000 kilometers, or 100 or 1 kilometer a second, depending on the type of gas. Pretty fast anyway. But slowly, and this is probably Maxwell who brought the theory to completion, is that he introduces probabilistic considerations. So he's the first one to assume that these gases, these molecules do not all have the same velocity, that they actually bounce off each other, and that particularly because of these collisions, which might be head-on or glancing, the velocities amongst the particles will change, will be changing all over the time. And that the best we can do is ask how many particles move with a certain velocity and how many particles move with another velocity. And that we could describe this in terms of a probability distribution, just the way in which 10, 20 years earlier, Catalan and other people have been using probability distributions to describe the distribution of attributes amongst the population. So it's a statistical or frequency interpretation of probability that Maxwell is using. And that was in 1860. So now I sort of come to the description of the theory. What we need to assume is state space, and following Ehrenfest, I will call that so-called mu space. Which is the state space of a molecule. In other words, if we assume that the molecule is just a single monatomic particle, then its state is described by a velocity and a position. So it's a six-dimensional space, and every point in that space, so this is mu, will give you the state of one particular molecule. The molecules are more complicated, state space gets more complicated too. Let's not try to make things too difficult at the same time. But that's just a single molecule. The gas will consist of many, many molecules, and each of them will have a different position and possibly a different velocity. So, amongst that single particles, we will have a whole cloud of particles. And the idea now is that we will introduce a probability distribution, or let's introduce a distribution function which we'll call f, such that that value gives us 1 over the total number of particles times the number of particles with velocity between v and v plus dv and position x between x and x plus dx.
Shouldn't those be volume elements?
I'm sorry?
Shouldn't those be volume elements rather than...
Yes.
So it's in the box d cubed x rather than between x and x plus dx.
It's in this box, yes. This is, well, my notation for the three-dimensional bill. And of course, we know, or Maxwell is fully aware, that in reality, because this is a discrete function, there is only a finite number of particles. But if that number is large enough, if the boxes are not too small, then we can approximate this by a continuous and smooth function. At least we will not make too large of an error if we do. And although this cannot be literally right, nobody in the 19th century, as far as I know, actually worried about it in great detail. It's the type of approximation that people made in physics all over the place. And again, I mean, if you have nothing else in your hand, this is the first natural, easy assumption to make. So this is typical for kinetic gas theory, that you try and describe the gas by means of this distribution function. I should say that this is not the only interpretation of the distribution function around. I'll come to that, I guess, when I need to. But typical questions that one can study now are, for example, what is the particular distribution that would correspond to a gas being in equilibrium? Or, if the gas is not in equilibrium, that is to say, if it's still changing its observational properties, how would that distribution function change in the course of time? Can we give an evolution equation for it? Those are typically the problems of kinetic gas theory. There's, of course, also, in terms of the distribution function, there are, of course, limitations of the theory. Because since the distribution function only tells us how many particles there are with certain properties, it will give us no information about how they interact or whether there are correlations between them. So you would need to go beyond that in order to incorporate it. Now, here is statistical mechanics, another theory, at least today we recognize those two things as different theories, because it employs a different description. And in this case, we will start out with a state space is the phase space. which is now the state space of the entire gas. That is to say, if this is gamma, and this is a single point in that space, then that point will give us the positions and the momenta of all the particles in the gas. This contains all the information you could possibly give about the mechanical state of the gas, not just a single molecule. And of course, at least in Hamiltonian statistical mechanics, we assume that there is a Hamiltonian defined as a function of state space, and that will mean that in the course of time, such a state will follow a particular trajectory, and we can solve the equations of motion, at least if we, in principle, they are solved. But now, once again, we want to introduce statistical considerations on that. And we do that by introducing a probability distribution or distribution function, which will have the property that if I take any particular, or at least smooth region A in phase space, it will have the property that rho x dx is the probability to find the system in region for the state of the system. Now, the problem is, in this case, I can sort of determine the distribution function, maybe only approximately, but still, by looking at the gas. The physical description of the gas tells me how many particles there are, where they are, how they're moving, and if I have that information, I can make up that number, that function f. The function f itself, so it describes molecules. It's a function over the state of molecules. But the function itself is defined by the state of the gas. Here, I'm introducing a probability distribution over the states of the gas. How do I find that function? Well, not by looking at the properties of the gas. I have to appeal to something else, something on a higher level. If I want to maintain a kind of a frequency interpretation, then what people do, and this is, well, this is actually what's done by Gibbs and also by Boltzmann at some point, is that you assume that apart from this actual state of the gas, there is a whole lot of other gases that sort of have been prepared in a similar way as my actual gas. and that this probability distribution should be thought of as the relative number of those other gases that you will find in that particular region A.
Jos,
Yeah.
I mean, this is a claim about the world that the theory is committed to, that there's always a bunch of actual gases.
No, they're not
these are
actual.
possible ones.
Okay, good.
They're, as Gibbs, well, in the case of Boltzmann, it's not clear, of course, but in the case of Gibbs, what he says is that they're figments of our imagination.
Okay.
We are simply imagining that apart from the real gas, there are all these other, and there's an infinite bunch of them, and that this distribution function represents how many, or in relative sense, of those systems have properties, have their states in particular.
So it's a claim about what kinds of gases prepared in this way are physically possible? I mean, what kind of a claim is it? Or am I supposed to read it as a claim at all? Or what?
I don't think so.
Or it's just it's a step in a set of instructions about how to calculate a physical
I
result.
think it's actually more a mental picture that will help you to you know, get an intuitive picture about that probability. It's not necessarily claim about the world.
I just want to make a comment. I mean, now we're at the end of the 19th century, early 20th century, and frequentism has become the dominant interpretation of probability.
Right.
And you know what you just asked are the questions people always ask about frequentism. Are we talking about actual
Good.
things? Is it hypothetical? If it is a hypothetical ensemble, what's the status of that?
Right. Good.
I see more questions.
Can I ask another question that people always ask about frequentism? Which is what's the reference class here? So what's the what individuates the way the gas is prepared?
Good question, and Gibbs certainly didn't have an answer to that. I mean, a systematic answer. Of course, I might try to give some suggestions, and so, for example, if that we can say the gases we actually look at in the laboratory have been prepared under certain macroscopic constraints. For example, they are prepared with certain energy, and that's all we know about them. We don't know where the particles are, but we do know that their energy is given, or in a certain range. So let's actually look at all other possible states, other possible preparations we could have been made for us with that same energy constraint. And then we will have the ensemble, which is more or less what David described, the microeconomical one, in which you sort of pick the system at random from an energy hypothesis. You could also say, well, maybe we have prepared the system with a given temperature, or maybe we know something more about it. So we sort of try to pick the reference classes with respect to experimental information we might have, or
But it's not going to be unique for a given system.
no, absolutely not. No, I mean, it's not like Gibbs solved the reference class problem of probabilities here.
So I want to make a suggestion. I think the status of probabilities in Gibbs and all these guys is kind of murky, and several of the talks later are going to talk about that. So
Okay. Look, I'll keep it.
maybe we because there's a lot I want to hear from you that I want to make sure we get to this morning.
Good.
So this is a probability question, but it's related to the history, so hopefully I'm not stepping on any toes. So it seems like, I mean, at least in the kinetic theory, it was a kind of hypothetical finite frequentism view. But then when you spoke about gives you.
So the finite hypothetical frequency?
Well, yeah, or actual. But at least the important thing was that when you started talking about Gibbs, it seemed as though now there was a shift towards a kind of an infinite, a move here to the infinite, and not just kind of this being an approximation given some large kind of finite. Is that something that was Gibbs the first to make this move, or were other people also flirting with the infinite idea?
No. Let me. I mean, if I restrict to the context of the authors I'm supposed to talk about, let me say Gibbs is the first one to do everything in a clear and systematic manner, and so he writes down explicitly what he needs. And yes, it's an infinite sequence, and it's called the ensemble, of course. Maybe you all know that. In the case of Boltzmann, does he write about infinite sequences of systems? Yes. Does he write about infinite number of particles? Yes. Does he actually mean what he writes? That's something that people have worried about. I mean, let me, it's something I probably want to say about Boltzmann anyway. What is sort of typical for his writings and what stands out and puzzles people even today is the rather curious love-hate relation he has with the continuum and the distinction between finite and infinite. There are, for example, many cases in his writings where he considers a gas with a number of particles n, and Boltzmann writes say so n is infinite, so it's an infinite number of particles. And then he says, and let dn be a differential of that. Now this, of course, is sufficient to drive any mathematician up the wall, to assume that that this number is infinite and that subsequently you can form a differential over it. Conceptually, it's also not straightforward because, if anything, number of particles is going to be a natural number, and it's not something you can form infinitesimal differentiations. Answer, of course, Boltzmann is only sort of hand waving. You don't necessarily interpret everything he says literally. But many people say, he says n is infinite. He just means it's very large. And this is although just some proportion of the number of particles that is small with respect to the total number. So he sometimes writes infinite. Very often he writes infinite. Doesn't really mean it. Curiously, maybe the other side of the spectrum. So he's treating quantities like numbers of particles that are naturally discrete in the form of a continuum. At the same time, he takes quantities like energy, momentum, and time, which we are commonly used to as thinking of continuums, and tries to treat them as discrete. And in those points, he says he has a distrust of the continuum, that he thinks that the continuum is only an idealization and that everything is discrete in reality. And he doesn't want to use differentials, and he doesn't want to use integrals, but he also always replaces them by sums. It's just a very particular attitude, and well, I guess I'm saying more than your question asked for. When reading Boltzmann, Boltzmann is not the type of person to ask, like, do you really mean infinite or do you really mean finite? I don't think that was a question. Distinction was certainly on his mind, but it's not a question that he worried about in the sense that we would worry about. Okay.
Sorry, before you continue. Regarding the variations that conform the many configurations that are in the ensemble, that Gibbs talks about, well, first of all, they all are supposed to be restricted to obey a unique Hamiltonian?
Absolutely.
Okay, so
yes.
Each follow the same dynamics?
Yes, yes. They're supposed to follow the same. So they're copies of the original system, which only differ in the sense that their initial state is different. But they absolutely have the same Hamiltonian, and therefore will evolve in similar ways as the original. The point is, so there are absolutely different interpretations of probability you could use in statistical mechanics. The point is that here, that distribution function was at least thought of as being determined by the properties of the gas. Once you know the distribution of molecules in the gas, you will know the distribution function. And it has nothing to do with knowledge or without degrees of belief or anything else, at least in the first natural work. Here, all the properties of the gas are already contained in that particular state X, the black dot here. Now I want to know something about the probability density. Well, in any sense, you interpret it, it's something you will have to add to the theory over and above the mechanical properties of the system. It is supposed to be an independent ingredient because there's no way of looking at the gas and saying, oh, it's in state X, and now tell us what rho X is. There are different ensembles from which that single state could be drawn, and therefore there are also different probabilities I could assign to it. It's something, I have to appeal to at least something else in order to be able to talk about it. And so here, probability is sort of determined by the mechanics, but here, probability is really an independent notion. You have to stipulate something about it. Okay, that was actually just the conceptual distinction between the two theories that we, or at least I, would like to make today. It's not necessarily a conceptual distinction in Boltzmann's work. Boltzmann, I would have to say, is not, he's probably one of the most prolific authors I know of. He's not the most systematic author. He has written more than 100 papers on the theory of gas. Some of them employ kinetic theory, some of them employ methods that would distinctively seem statistical mechanics to us. And to be frank and short, I mean, Boltzmann is the type of guy who is more or less opportunist. He tries out a particular line of thought in a certain paper. Sometimes he's happy, sometimes he's not, and then he drops the idea, tries out something else, and sometimes 10 years later or so, he suddenly comes back to a type of approach that he dropped 10 years before and starts to extend it, and he shifts his approach, he shifts his assumptions or the way in which you would try to approach the problem all around, and from paper to paper, sometimes within the papers, and it's a formidable amount of work. And I also have to say, I mean, those were the days in which once you were established as an academy member, you could have your papers published without any refereeing at all. And Boltzmann, I think, more or less wrote papers like somebody would write their diary. And in the middle of the course of an article, he could suddenly think, oh, let's try something completely different. And having given no warning in the beginning of the paper, like, I mean, there were no abstracts. I mean, there were no referees saying, give an abstract to this paper, saying, in this paper I will do this and this and this, and I will conclude that. No, sometimes you have to read through the whole thing, and then suddenly discover that there is some brilliant insight in the last pages. Boltzmann is not the easiest author to understand, and he was actually the father of many different types of approach to the problems of gas theory. And this is confusing because nowadays there are still many people who would like to take Boltzmann as their champion and say, we are developing this particular approach which was founded, and this is the original thought of Boltzmann that we are representing and defending in the world. You will find another approach to statistical mechanics, taking a completely opposite point of view and competing with the first group of guys. And they say, we are defending the views of Boltzmann, and therefore we take this completely different approach.
It's the physics version of Wittgenstein.
And are they both right about tracing back their ideas to Boltzmann? Yes. But in Boltzmann has all these opposing different thoughts, and he never clarified or never presented a systematic theory in saying these are the fundamental assumptions we should use, and we should solve all our problems using only that set. So, I'm not sure how I'm doing on time. If you can tell me when we need to break.
Well, 11 o'clock would be about halfway through.
Good. I cannot, of course, give you any representative part of what Boltzmann was doing. But I will try to tell you at least some of his most important papers. And I'll try to be as quickly as possible. So Boltzmann wrote from, these papers range from 1866 to 1904. I said there were about 100 of them, there are 3,000 papers. There are also a couple of books you might wish to look at. And In his very first paper, Boltzmann tries to give a mechanical reduction of the second law of thermodynamics. He wants to find a theorem in pure analytical mechanics that would correspond to the second law of thermodynamics. Now that project was not very successful. I should also say that by what at that time what he meant by the second law of thermodynamics is only the part that is concerned with reversible processes. Therefore, he has no problem at all with irreversibility because he simply doesn't consider it. This project failed, but the problem stayed with him. And the next important paper was from 1868, when Boltzmann adopts the kinetic theory of gases. And it's quite clear how he got that, because he has written Maxwell. In fact, it's well known he was supposed to, he had to learn English in order to be able to read Maxwell, and he did so. And after reading how Maxwell talked about his distribution function, Boltzmann said, oh, I'm going to do that too. And he was trying to extend and improve Maxwell's presentation and apply it to a whole host of new, slight variations of the original problem. But so here's what he did. You have these particles, and so we suppose that there are these particles are hard spheres. And we want to know how that probability, how this distribution function would look like in the case of an equilibrium state. Now, there are many ways in which you want to go about it, but one of the defining and characteristic properties of an equilibrium state is that as long as the system is not intervened with, it will stay stationary in time. So the question is, when is this probability stationary in time? And we also introduce another simplification, and that is that this distribution function is actually uniform in position, so the gas is sort of evenly spread out all over the volume, and the only variation is in the velocity argument. So this is a more simple distribution function that depends only on velocity. Now, how does that distribution function change if there are hard spheres? Well, it changes under the influence of collisions. So I have to say something about how particles are colliding in order to see how that distribution function changes. And here there is what is known as the Stosszahlansatz. This is not a word introduced by Boltzmann, but it had been coined later by the Ehrenfest. This is an assumption about the number of collisions. And it takes the following form. A collision, since we're only interested in velocities, would be something of the following form. You have two particles, a pair of particles, moving with velocity v1 and v2, and these are all vectors, of course. After the collision, they would be moving with different velocities. So consider collision. So what would happen is simply we've got two particles. This one's moving with v1 and this one's moving with velocity v2. And now they collide and they move. In other words, and this is the velocity after the collision. After that. We want to know how many of those collisions occur, where of course the final velocities are determined by the initial velocities and some geometrical factor about whether it adds on or glancing, or depending on the shape of the molecules, they will come together. We need to know something about how often these collisions happen to determine how many particles with given velocities are changed into particles with other velocities. Now, the basic assumption that the number of collisions of this type is proportional to the product of the relative number with velocity v1 and velocity v2. The number of collisions of this type will simply depend on how many particles of type v1 there are and how many particles with velocity v2 there are. Okay, having done that, we are very close to finding a stationary distribution function. The only thing we have to consider is so a sufficient condition for stationarity is that the number of collisions that go this way equals the number of collisions that go the other way. Because for every dynamically allowed collision of this type, there is the so-called reconstituting collision, in which initially there are particles moving with velocity v1 prime, v2 prime. And now they go back outwards with so for every collision of this kind, there's another collision in which before the collision the two particles have the same velocities as those particles have after the collision. And after the collision, they will have the same velocities as those particles had before the collision. The only thing is you have to change left and right as well. This is, of course, the simple application of CPT invariance. Now, that's just a dynamical fact about the theory. What I'm assuming here is that there will be a stationary distribution amongst the particles if the number of particles go one way is equal to the number of pairs going the other way. And of course, that will happen under this assumption if the number of particle pairs going one way, which is proportional to Fv1, Fv2, is equal to the number of particle pairs going the other way, which would be the product of their function for their initial velocities, which was I'm skipping some of the more complicated stuff about the geometrical factors and stuff like that, but that works all out very fine. And this is, at least in 3 dimensions, the condition that would be sufficient for stationarity. This was already done by Maxwell. And Maxwell observed that as these particles all have the same mass, and therefore there is, of course, a condition for the conservation of kinetic energy. Particles don't feel any external potential. And that condition is that this must always be true. And knowing that, you can see that this is fulfilled if Fd is of the form of an exponential of v squared, because then this condition becomes equivalent to this condition, which is true. So this was what Maxwell did, and he concluded from this argument that a function, distribution function of this type, will always be stationary, and that therefore it is a possible candidate for the description of equilibrium. Yes?
Is that sufficient or also a necessary condition?
That's the next question. Maxwell wanted to argue that it's also necessary, but he had to fill in 2 steps to do that. First of all, he would have to show that this assumption was not only sufficient but necessary, and he would have to show that this function is not only a function that satisfies this, but the only type of function that satisfies it. For the first type of problem, Maxwell had an argument that is not very convincing, and certainly Boltzmann didn't buy it. For this next step, Maxwell had no argument at all, but Boltzmann provided one. And he showed that this is actually true, that this is the only type of function, this one. That still doesn't solve the entire problem because, and this is still an open question, this is not necessarily true. This is now called the detailed balancing condition, which, by the way, would also form an excellent topic for a research project because there's not enough consideration of it. So this is what Maxwell does in his 1868 paper. It's a fully set within the kinetic theory of gases. But then, at the end of the paper, he suddenly changes gear and introduces statistical mechanics. He says, you know what? I've got a method that will give us the same result in a much more general fashion. And what he there exposes, he says, let's take an arbitrary Hamiltonian system, which will have a Hamiltonian which is just the sum of the kinetic energy terms plus an arbitrary potential energy. So this is not necessarily a gas. This is an arbitrary mechanical system. This is not necessarily a hard sphere gas. Could be anything. And let's make one particular assumption about it. Suppose if we solve the equations of motion and we determine the trajectory of the state through its allowed region, which is a particular energy hypersurface, because energy is of course conserved. And so suppose that this trajectory traverses through every point of energy hypersurface. Then the proportion of time that xt spends in the region A in gamma, or on the energy hypersurface, is given by what we would now call the microcanonical distribution, which is just in a slightly different notation, the distribution function that David talked about yesterday with some normalization. That is to say, it's probability distribution which is 0 except on energy hypersurface. And on that hypersurface, it is basically a constant, except that it depends on the gradient of the Hamiltonian. So what happens is that this particle is confined to the energy, this state is confined to the energy hypersurface. But it will visit different regions of the energy hypersurface, just in proportion to the size of those regions. Yes.
Is the idea that x traverses through every point in the hypersurface
Absolutely.
shorthand for something like the path of that point traces out, passes arbitrarily close to any given point in the hypersurface?
Well, as I said, it's not always quite clear how literally you should read Boltzmann, but what he says is actually that it goes through every point of the hypersurface. Now, you're quite right to be skeptical about that, because even Boltzmann himself soon dropped this assumption. And when the Ehrenfest wrote about Boltzmann's work, they were equally skeptical. They pointed out how important, at least they thought, this assumption had been for Boltzmann. They said, well, but actually this cannot be realized. And very soon afterwards, 1913, there were two independent proofs of that this is completely mathematically impossible. But anyway, Boltzmann makes this assumption, which is nowadays called the ergodic hypothesis. Which is it. And then, if we are interested in how much time the state of the system passes through particular regions, it will be described by a particular probability distribution, which takes the now very familiar shape of the microeconomic. Yes?
So I think you started this by saying that it was unclear, at least to begin with, whether, this should be understood as, say, applying to any system.
Absolutely.
I take it though, Boltzmann thought about this with relation to a particular system. Is this one of those instances in which the ergodic hypothesis was something that it's unclear as to whether he thought this applied to every system, or is this one of those instances in which we should understand him more literally, in that he was actually making this claim of any system?
It's an excellent question. I think Boltzmann is as clear as one could desire about him. He says this is a hypothesis. He admits immediately that it's not proven, and that he doesn't know for whether it is fulfilled for any particular. But it's an assumption that helps him drive again at a very desirable conclusion. But he immediately admits that this is a weak spot, that he makes as an assumption, but that he doesn't know how to motivate or justify it. Does that answer your question?
Yeah, I mean, I suppose because I know that there are systems for which this is false. I'm just curious as to whether he was optimistic that a proof could be of this could be shown, or whether he was kind of, I suspect maybe there are these systems that are not.
Well, the short answer is, or maybe it's the wrong answer. In this 1868 paper, he admits that this was an hypothesis. He says, I know there are counterexamples, because, for example, if the energy hypersurface was something like this, what would be needed is that something like that trajectory would literally cover through, visit all regions and do something like this. And even that might not be sufficient. He knew very well that there are, but those trajectories are really very unstable. There only has to be one tiny particle that happened to fly by the system and disturb it ever so slightly. And then, if there's a small perturbation on that trajectory, it will no longer be closed, but it will, it will go something like, doesn't actually intersect itself, it will go wild all over the place again, just like I wanted. So he says, yes, there are counterexamples. They are very unstable. I only have to assume that there are minute perturbations on the system, and then my counterexamples will go away. So he ends the paper in quite an optimistic note. There's apparently a remark written in pencil in his own handwriting in the margin of that very final page, in which he says, oh, well, I've argued that my counterexamples might go away, but I haven't actually proven the validity of my hypothesis. And there is the next couple of papers in which he sort of investigates the whole idea. But then very soon, in 1871, the whole idea of the ergodic hypothesis drops out of favor. And he starts to explore other avenues. And he doesn't come back explicitly to mentioning the ergodic hypothesis. But once he, again, gets at results that will show that the Maxwell distribution has to be of this form, he writes, this time I've arrived again at that result, but this time I have not used any hypothesis at all, which is going to which shows that he has become doubtful of the ergodic hypothesis, and he never uses it again until the 1880s, when it suddenly reappears in his work, and he starts to use it very heavily for a couple of years in a few papers. And that's actually only the time when the term ergodic actually made its entrance into this field. Does that answer the question?
I mean, just to answer it a little more, it's easy to think of examples, right? I mean, you have a bunch of particles in a perfectly rectangular box. You start them off in a state where they're all in one corner of the box and their velocities are exactly parallel to one another, and they just bounce up and down, okay? First point, this is obviously not an ergodic trajectory. Second point, this kind of trajectory is clearly very unstable. If one of them is going at even the tiniest angle, eventually it's going to start bumping into the others and messing everything up.
Yeah, that's exactly what he means. Yeah. Of course, there are also examples which are ergodic, and the most simple one would be the one-dimensional harmonic oscillator, where the energy hypersurface is just a circle, and the trajectory actually goes to the circle just as well, and it visits every point of it. And there, everything is hunky-dory. But as was later shown, as soon as you have a energy hypersurface which has a higher dimension, then it doesn't work that well anymore. And in particular also, if you would have any conserved quantity independent of the energy, the ergodic hypothesis would fail too. Let me just try to finish what I was trying to say. In this last section of his 1868 paper, he introduces this hypothesis, which, as we have well established, is dubious. But he also introduces a method looking at not the distribution function over molecules, but looking at the entire mechanical phase space, introducing a probability distribution over that phase space, which is an extremely complicated object, but it's basically exactly the calculation that David gave us yesterday about the volume of a hypersphere in many dimensions. Boltzmann goes through all the works, and what he now considers is to take a marginal, so x of course is still positions and the momenta of all the particles. And what we can do now, we can take a marginal distribution.
It's the first time I've ever
But at the same kind of conditional on the positions. That is to say, we will consider the x component of the momentum of particle 1 given the positions of all the others. That probability distribution, of course, is obtained by taking rho x and then integrating over all the other variables, which would be dp2 to dpn and dp1y and dp1z. So I'm getting rid of all the momentum variables except the x component of one particle. And I'm taking the positions as being fixed. Now, this calculation has been shown yesterday by David, and Boltzmann gets exactly the same result, namely that if n goes to infinity, this is going to be proportional to v1x squared divided by a function that we call kappa, where kappa is just the total energy minus the potential energy. So that's actually the only place where the dependence on the positions appears. Now, should we restrict ourselves to a case in which there is no potential interaction between particles, so that this term is a constant, or at least a constant inside volume, then the dependence on the positions would become completely trivial, and we can forget about them. If there is interaction, then there is a dependence on position as well. But if we go back to that former case, then this is easily recognizable as a variation, a slight generalization of Maxwell distribution, because this is still quadratic in the velocities of the momenta, and in fact the denominator is just the average, the kinetic energy, but now divided, total kinetic energy, but now divided by the number of particles. So this should be capital F. So, Boltzmann's very happy. He says, look, I don't actually need all these assumptions here about hard spheres. I don't actually, well, not quite so explicit, but this is of course the message. It doesn't actually need to rely on assumptions about collisions. Maybe the particles don't collide at all. There's no assumption about that here at all. We only have to make this innocent hypothesis, and then we will get something which looks like the Maxwell distribution all over again. So it's not like this distribution is restricted to this particular gas model that Maxwell assumed. It has a much more general application. There's one final remark, and then I'll shut up. There is, of course, a shift going on, because here we were talking about probabilities that represented the number of particles with a certain velocity. This probability distribution is a marginal conditional probability distribution of something that had the interpretation as the proportion of relative time that the total system spends in a state in which P1x had a certain value. That is not necessarily the same thing as the relative number of particles. There is no guarantee in general whatsoever, unless this thing happens to be symmetric under the particles, whether this would be the same thing for particle 1 and particle 2 and particle 3, etc. So it's something which, unless we make further assumptions, has quite different properties. Is that a big conceptual step that Boltzmann comments on? No, not at all. Because there's one more thing that I wanted and must have said about this particular paper, and in fact it's something which is constant all over Boltzmann's work, and that is that he changes his interpretation of probability as easily as you would change clothes in the morning. And sometimes he does that within the same sentence. So
That's even easier than I change clothes.
yes. So what he, where was it? When I said that in the kinetic theory of gases, the distribution function, oh no, this is this one again. The distribution function represents the relative number of particles. That's the idea that Maxwell had, and Maxwell was consistent and used that idea only. Now, Boltzmann is following Maxwell, so he has this idea also. But at the same time, he thinks that that very same distribution function also represents the relative amount of time that the particle spends having its velocity in a certain range, or its position in a certain range. So he uses relative time interpretations as well as relative particle number interpretations of probability. And as I said, he says this function has this particular interpretation. Therefore, it represents the relative amount of time that the particle has. It's quite striking, and as far as I can tell, this is something you find in his first paper, something you find in his last paper, and you can find it all over the paper. Not in every paper it's as striking or important as in other cases, but it's a striking equivocation, and this was something that sort of glared out to the Ehrenfest, and they made that the central problem in Boltzmann's approach. Are phase averages or particle averages the same thing as time averages? Boltzmann certainly almost shrugged his shoulders, and as far as I can tell, he just didn't see that there was any probability. But just because already in the first stages of this 1868 paper, he uses particle averages and time averages on an equal footing and changing easily between one and the other. When he gets to the final pages, and now he works in statistical mechanics, he doesn't actually introduce an ensemble here. The probability distribution he gets is the time average. In this case, not of a single particle, but of the single state of a gas. But it's still something determined by the gas. It's not something for which you would need to refer to an additional ensemble. That's why he could get that, because he was thinking of time averages all along. But still, a large proportion of the machinery of statistical mechanics was already given in one of Boltzmann's very first papers. Now you might think that, oh, maybe he will continue in trying to develop statistical mechanics. No, as I already mentioned, the ergodic hypothesis soon fell out of grace in his thinking, and maybe therefore the entire machinery of statistical mechanics fell out of grace, and he would continue working in kinetic theory for actually maybe most of his work, sometimes going back and forth between them. But there's no clear watershed in Boltzmann's writing anywhere between kinetic theory and statistical mechanics. That is not a distinction that bothers him very much. And he would continue using both approaches, just as whatever he thought was going to be most fruitful at the time that he was working. That's time for a coffee break.
Time for a break?
And certainly one of the most famous ones. And this was from 1872, where he goes, remember, Boltzmann started out with a project of trying to relate the second law of thermodynamics to mechanics. He sort of dropped that for a while after he read Maxwell. That gave his first start in kinetic theory of gases and a first exploration into what we would now call statistical mechanics, ergodic hypothesis. Okay. All of that is merely considering equilibrium states. It is about finding conditions for and a characterization for what distribution of velocities you would have in a thermal equilibrium state. In 1872, he starts to consider non-equilibrium states. He drops the ergodic hypothesis and any statistical mechanics machinery associated with it, goes back to the kinetic theory of gases in terms of a distribution function. But now he wants to know how does Fp change over time. Again, you will find that that distribution function is at the same breath supposed to measure how many particles there are with a given velocity. Also, he writes about it as if it's the time average in which a particular particle has that particular velocity. But that particular, although he gives that interpretation, he doesn't actually use it, and probably for good reasons, because if you average over time, then you get something which doesn't depend on time any longer, and therefore cannot change. So he doesn't want that interpretation on this particular occasion. So think of this as the number of particles with a given velocity. And we want to know if this is some arbitrary initial shape, how that shape will change over time. And we are assuming the hard sphere test. So the particles are tiny billiard balls moving free through space, only colliding occasionally. Now, as we said before, the mechanism for how this function could change is mainly the collisions between the particles amongst each other. And Boltzmann had been using this assumption already, which he picked up from Maxwell. That is to say that the number of collisions of this particular type would be proportional to this particular product. And from that, it is a relatively simple or straightforward or intuitive way to get a consideration which will give an answer to this. And that is as follows. So how does this distribution function change? Well, so the change of, let's say, Fv delta V in time delta t, it contains two contributions. There's a loss term because of collisions. Let's tell this V1. If there are collisions of this type, where the final velocities are different from the initial velocities in general, then every time a collision like this happens, the number of particles with velocity v1 are destroyed, so to speak, and reappear as particles with a different velocity. So that would mean that Fv decreases every time a collision like that happens. How many of those collisions are there? Well, we already said it's proportional to that number. But there's also a gain. That is to say, there were particles that initially had different velocities from v1, but after a collision, they get the velocity v1. That would raise the number of particles with that velocity. What are the particles that do that? That are precisely the reconstituting type of velocities. So, what you get is that the change of this distribution function is going to be proportional to delta t. There's also an n, which I will not talk about. But in particularly, there is this factor. This is the loss term, and the number of times collisions of that type happen. This is the gain term, and therefore it has a plus sign in front, and it's about the number of constituting collisions that result in the velocity v1. And so Boltzmann sets up the following equation for how the distribution function will change over time, and it's simply the integral over all the other ranges for the velocity of the second particle, and an integration over the geometrical vectors that I want to jump over. And then there is this particular integrand. And as it happens, if the difference in velocities is larger, there are more of those collisions happening in a particular time. So there's also this integrand. And that is the famous Boltzmann equation, at least in the special case in which we assume that the spatial distribution, spatial dependence of the distribution function is uniform. And as David correctly pointed out, this is a very important result that is used every day still in many applications in physics. It's really the workhorse of kinetic theory because it gives us a description which goes way beyond thermodynamics. It gives us a qualitative description about how things change when they're not in equilibrium, whereas thermodynamics only tells us that there are equilibrium states, and if the system is not in equilibrium, then it will approach equilibrium. But how fast things change, what relaxation times are, thermodynamics says absolutely nothing about that. Kinetic theory apparently is able to give us some qualitative information. So good, important result. Problem is, it's a hell of a complicated equation, and because it's nonlinear, and that's only perhaps even the smallest of our problems, but we don't know in general whether the initial value problem is solvable. That is to say, if you would give me at an arbitrary instant a shape of f, and you would tell me that it had to evolve according to this evolution equation, it's an autonomous evolution equation, so the change is determined only by that function itself. But how you can explicitly solve it, in fact, question whether there is a solution and whether it's extendable through time, are extremely hard. In fact, Hilbert put the question of solving the Boltzmann equation amongst one of the 10 famous problems that he thought had to be solved in the 20th century. Well, there has been progress on the topic, but the answer is not known in generality. And one of the great problems that it's very hard to get grips on, mathematically speaking, is that apart from its nonlinearity, there is of course an obvious side constraint, and that is that since these functions f represent physical distributions or probability distributions, they would better remain positive. And it's not known. I mean, in general, it could very well happen that you set up an initial problem try to solve this equation, and then at a later time discover that the evolution develops into functions that are negative and with certain ranges. That would be physically completely unacceptable. But whether that happens and whether you can actually avoid that, nobody knows. Still, it seems to be the case that there is a lot of useful information you can extract from it. And Boltzmann himself, although he clearly was not able to solve this equation by any means, he could derive one particular very interesting result, and that is that if you define a quantity which is functional on these distribution functions, and we suppose that these distribution functions, let me first say that this is at the logarithm at c. Suppose that ft is a solution of the Boltzmann equation. Then, and this is H theorem, this quantity will show monotonic behavior in time. It can only decrease or it can remain constant. And furthermore, it will remain constant for all time, if and only if this is once again something proportional to the Maxwell distribution. As you can easily check, because if that we take that, we already established that those two factors would be the same for the Maxwell distribution. So the integrand vanishes for all velocities, and therefore the Boltzmann equation gives you a trivial evolution. F doesn't change. So, without actually solving the Boltzmann equation, we could use it to establish the validity of this theorem. And this is rigorous. There's no further approximation or silent assumptions that have to be used over here. So now Boltzmann is very happy. Remember, he wanted to relate the second law of thermodynamics to mechanics in the first place. And now he says, well, H, let this be entropy, or actually we now say up to a constant, which Boltzmann didn't have, and is therefore known as Boltzmann's constant, and a minus sign, which is probably due to well, some freak incident in history that he didn't include the minus sign in his definition. And that it would have then is that if this is the entropy of the gas, then that entropy could only increase during its evolution until it obtains a maximum value, which it reaches when this is the Maxwell distribution. So Boltzmann says, now I got a complete, rigorous, analytic, mechanical expression for the second law of thermodynamics. I've reduced that to mechanics. And that probably should have turned quite a few heads. So let me make a few remarks. And the first thing is that Boltzmann both overstates and understates what he had actually done. If we go back to thermodynamics, we know that there is a second law of thermodynamics, but it can only give us entropies for equilibrium states. The second law said if you start out in some equilibrium state, perform an adiabatic process, which might take the system out of equilibrium. But if it finally ends up in another equilibrium state, the entropy of that equilibrium state is larger than that of which the one we started out with. Thermodynamics required by no means that the entropy change between the initial and the final state was monotonic. In fact, precisely because entropy was defined only in equilibrium states, entropy is not something that can depend on time at all in thermodynamics. So when Boltzmann says, hey, this is the second law of thermodynamics, because I've got something that changes monotonically in time, what he's actually silently or almost without a single thought is doing, he's extending the notion of entropy from equilibrium to non-equilibrium. So he does much more than simply reproducing the result of thermodynamics. So Boltzmann actually extends entropy to non-equilibrium cases. The other thing, which may be less important but still, is that remember that in thermodynamics we talked about an arbitrary adiabatic process. An arbitrary adiabatic process is one in which there's no heat exchange with the environment, but in general cases there will be work done on the system. So the adiabatic processes typical cases would be where I've got a container which is thermally isolated from the environment, but there's a piston that could move in and out and do work on my gas system. Or there might be a partition that could be removed and make all the particles that were originally on one side diffuse into the other chamber. Or the other archetype of tidal system would be where there is a pedal wheel steering the system around. And in all of those cases, thermodynamics will say, the second law of thermodynamics will say, if you start out in an equilibrium state with a certain entropy, and you perform any of these processes, the entropy in the final state will be larger than in the beginning. Does Boltzmann consider any of these processes? No, not at all. He never considers work being done on the system or any change in its volume. He is only concerned with systems which are completely isolated from the environment. And maybe it's for that reason, to simplify history, that you will find many statements of the second law of thermodynamics as if it only applied to isolated systems. Because if that's your reading of the second law, then Boltzmann has done a good job of reproducing that and extending that in kinetic theory. But in all fairness, it should of course be mentioned that the original thermodynamical reading of the second law had a much wider implication than anything that Boltzmann did. So he does more, but he also does less than what he should have done in order to replicate the second law. So these are not considered. Now, apart from that, there is, of course, the foundationally interesting question that has caused more than a century, probably almost a half of debate, and that is that clearly the Boltzmann equation and the resulting H theorem imply irreversible behavior. There's time directedness in these equations, which is somewhat surprising if, as Boltzmann originally claimed, these were results that he obtained purely from mechanical considerations, since mechanics is obviously time reversible. This was an objection which was put to him in writing 5 years later by Loschmidt. And then there was a reply by Boltzmann, which I will skip over because it's actually very confusing, if not to say confused. And he admits at the same time that Loschmidt had made a very important observation. At the same time, he says that it's a fallacy that Loschmidt commits. He said that he had proven something quite differently than he had actually done in his previous paper. He said, I never proved that this must be a necessary consequence of my theorem. Of course, there are counterexamples. Well, in the previous paper, he just said that this is a rigorous, analytic, surefire result of pure mechanics. And so he tries almost all strategies in the rhetoric arsenal to answer Loschmidt, but I cannot say that there is any satisfactory answer to it. The problem resurfaced several other occasions. There was a discussion with Tate in the late 80s. And then most famously there was a discussion in Oxford, or in the columns of Nature, in 1895, where Boltzmann had given a lecture on the same type of stuff. And people started to ask, where does the irreversibility in this theorem come from? Certainly it cannot come from mechanics alone. So there must have been at least one particular assumption that was sensitive to the direction of time. Where is it? Well, as we now know, it is originally, it's in the Stosszahlansatz, which originally seemed perfectly harmless in the hands of Maxwell. But then Maxwell was only considered with equilibrium to begin with, and not with arbitrary distribution functions. But now Boltzmann has considered non-equilibrium states. And even in those cases, he still thinks that the number of pairs of collisions of this kind is going to be proportional to the product of the relative number of these particles, expressed in the pre-collision velocities. So this number of particles, number of collisions, is going to be proportional to numbers of particles with those velocities just before collision. And that is sensitive to the direction of time. Because now we distinguish before the collision from after the collision. We could, for comparison, also have demanded that this number was proportional to the product of those functions, but now for the velocities after the collision. Had we done that, we would have obtained a minus sign in our Boltzmann equation. We would have picked up a minus sign over here, and we could, what's now known as the anti-Boltzmann equation, we could get a decrease of entropy as a universal consequence of this theorem. That's where the irreversibility enters. And it took people a very long time to even start to see that. Boltzmann certainly was absolutely not aware of that he had made an assumption which might seem dubious, and whatever it was an assumption which did not only, it's not a consequence of mechanics. Whatever motivation you give for the assumption, it has to go beyond the validity of the laws of mechanics. Yes?
Well, perhaps just on that, do you think that there is a suitable justification for the Stosszahlansatz?
I would hope so. Well, perhaps I could say something about the possible strategies that people have taken. Let me add one more point for your information. And it is not just that I have to assume this, say, at the initial time, and that then everything will take care of itself. No. I have to make this assumption for all times, because only then do I get an equation, an evolution equation that is not restricted to a single time, but will in fact hold for all times. So it's not something that you could easily think of as being due, but so this is our first strategy. Maybe this is all due to, not to the laws of mechanics, but to choice of an initial condition. What I just said says, well, it's not an initial condition of your bread and butter variety. It's something that has to hold for all times, and that would make a very, very, very stringent condition.
Yeah, it might be a good point to comment that for an isolated system, it can't hold for all time because of the recurrence.
That's true too, yeah. What other types? So it's certainly not guaranteed by laws of mechanics. It's also not going to hold for all times for any initial state, perhaps for a measure zero subset of phase space. Could there be some other explanation? I guess that many people have thought of it as being related, and Boltzmann also sometimes suggests things like that, related to a particular conception of causation over and above mere mechanics, in the sense that we can have a sort of causal principle about the type of processes that occur in nature, which brings it about that any two particles that are going to take part in the collision can be regarded as independent in a statistical sense, namely as uncorrelated before the collision, but not necessarily after the collision, because their interaction might produce mutual dependency.
But Jos, that would be, let's see, if that's not equivalent to choosing initial conditions, I'm confused. There are going to be certain solutions to the Newtonian equations of motion in which that's not respected.
Absolutely.
So either it's a denial of the truth of those as dynamical equations, or it's some kind of restriction that would amount to a restriction on initial conditions. I take it.
It would,
right? That is, we have a space of possible solutions to the equations of motion. That space of solutions includes solutions that respect the criteria you just described and ones that don't.
Yeah.
So as long as the classical mechanics is in some way in place, I take it this amounts to restricting the set of solutions that you consider as physical.
Of course.
Right.
Yeah.
Okay.
Yeah. So let me put it this way. If I didn't appeal to causality, but said, oh, it must be due to initial conditions, then the fact that it's going to have to be valid, or at least maybe approximately valid for all times, will put a very, very, very heavy restriction on the initial conditions. That is just a fact, but many people would seem to say that, well, that's a very stringent condition, because now I have to pick such a special set of initial conditions, and I have to ignore all the other states in which our system could have been. That seems highly arbitrary. If I have an appeal to causality, I could say, and I impose a principle that goes over and beyond mere classical mechanics, then yes, I would have to restrict the set of initial conditions. That's a way of representing that principle in mechanical terms. But now it might be that the class of initial conditions that would satisfy the Stosszahlansatz is actually a very large set in the thus restricted. And then I might conclude, oh, maybe this condition will typically be that.
Right. Right.
What did you mean when you said appeal to causality?
Well, I'm thinking of principles like Reichenbach's principle of common cause, which, at least in some formulation, says that, correlations can only be produced by interactions, and that things that have not interacted before, so before the interaction, before the collision, the probability of finding a pair of particles with velocity v1 and v2 has to be this one. There are variations of that. There is Reichenbach's fork asymmetry principle. There is Price's principle of what he calls microscopic innocence.
Micro-innocence.
Yeah. So he said before the collision, particles don't know of each other's existence, and therefore, since they have had no causal interaction, their probabilities must be independent. And there are other variations. Incidentally, on the few occasions where Boltzmann did comment on this condition, he was actually assuming that two particles that are about to collide might have had knowledge of each other by previous collisions in the past, but that past would be so distant, and in the meantime they would have met so many other particles he collided with it, that they must have forgotten all about it. So
hard to see
that is something that I would like to call microscopic promiscuity.
It's hard to see that the common cause principle is adding anything to trouble, because you narrow it down to the case at hand and you have the Stosszahlansatz. You expand it and you're now in this murky realm of all sorts of probabilistic cases where the probability spaces are undefined. So I think you're better off just sticking with positing the Stosszahlansatz directly than going with that sort of principle.
Absolutely. When I started to go down the list of possibilities of trying to motivate this principle, I was not in any way trying to suggest that I claim that one of these motivations is appealing, satisfactory, or that I adhere to them. I'm just saying that these are approaches which are around in the literature. This is how people have thought of maybe trying to get to grips with
To pick up also on just David's point, I thought you were saying one of the difficulties is you have to get it to work for all time.
Absolutely.
And so I imagine you had in mind there, this is the question there, you had in mind a justification where you would do something like showing that if the Stosszahlansatz is satisfied now, then it's satisfied delta t later and then delta t later. And you could maybe get some kind of a dynamical equation that is going to tell you how long that satisfaction is going to last. We know because of Poincare recurrence that every such time horizon is going to be finite. Right?
Yeah.
I mean, is that the sort of thing you think of? Because that would be one hell of a big operation to get that to go.
Good luck with that.
Sorry?
Yeah,
But-
good luck with that.
But, I mean, I
There's a
had
certain
thought,
sense of that with the Landford's theorem is doing that.
Yeah, well,
Okay, ignore that, Mark, if that's necessary.
I just, and maybe this relates to the last comment. For sure, if you wanted to hold for all time, that's going to be enormously restrictive on initial conditions. Yeah, very plausibly to a set of measure zero, and we would expect that because of phenomena of recurrence and so on and so forth. But my impression, and the impressions I get of what's been done in modern statistical mechanics is mostly from Shelley Goldstein, I guess. My impression is that from Shelley, that if you do a standard, modern statistical mechanical calculation, that is, you take a classical one, you take a macro state, you take the standard uniform distribution over microstates compatible with that macro state. You can get from that with overwhelmingly high measure, along those trajectories, the Stosszahlansatz is going to be satisfied or approximately satisfied for a finite but considerable amount of time. Does that conflict with your impression?
that's certainly a very desirable result. I do know, and this is Landford's result, that what you just described, under those conditions, you will get an approximate satisfaction of the Boltzmann equation for positive times. Unfortunately, the extent of the time duration in which this is proven is about a fifth of the mean time between collisions.
Really?
Uh,
That's not
which for a typical gas would be microseconds.
But is it thought to make it plausibly true for longer times, or are there reasons
There
why
are
it
people
wasn't cut
there are
off
people
there?
working on that,
Right.
and some results are there, but they are cases where there's a gas expanding into a vacuum,
Right.
large vacuum,
Right.
rather than one that is
Sure.
contained into.
Right.
And of course, if that happens,
Right.
collisions become fewer and fewer
Right.
and fewer.
Right.
And then it's easy to say, oh, Boltzmann
Right.
equation will last for a longer time.
Right. Right.
So I'm not so impressed with those
Right.
results. But that's the only case in which mathematically things have been working out better.
Right.
Of course, all of these results that have been obtained, and this is also what came up yesterday in data stuff, have the problem that we will get maybe what we want if we start out for some initial distribution and then ask, what does that distribution look like later? And we might get approximately what we want. But we could also ask, what was that distribution like earlier? How did it look like for negative times? And typically, what will be the case in any rigorous attempt to relate this result to mechanics is that you will get convergence to the Boltzmann equation for positive times, but you will get convergence to the anti-Boltzmann equation for negative times. Now, the Boltzmann equation seems to work perfectly well and is the workhorse of kinetic theory and seems to be perfectly in accordance with what we observe. But the choice of some time as being the initial time seems to be perfectly arbitrary. And the same machinery we use to tell us that the Boltzmann equation is in accordance with mechanics will also tell us that it will not be in accordance with mechanics for negative times. And that, of course, perfectly restores the time reversal invariance. But it doesn't tell us why the things that we observe in the laboratory are well described for positive times, but not for negative times. So there's always a puzzle that remains there. David?
It's just picking out that list. Quick observation, I guess, about the interplay between conceptual and mathematical issues here. I mean, if it was the case that we had a clear conceptual consensus that a necessary and sufficient condition for the Boltzmann equation to hold true of the systems it's supposed to hold true of, given the microdynamics and so forth, was that such and such ridiculously difficult mathematical problem should give such and such answer, then you could be inclined to say, well, the problem remaining is not a distinctively philosophical problem. We have confidence in that situation that it was highly likely the mathematical result did hold, or something in its close vicinity did hold, because we had an enormous amount of cases of non-rigorous but highly persuasive evidence that the mathematical result was true, of the kind that we actually have all over maths for things like P's and NP and the mean hypothesis and so on. Because we're not in that situation, it's not as if there's any conceptual consensus that a given mathematical result, were it to be proved, would deliver everything that we want in this situation.
I find that it's hard to see what you're getting at and what your diagnosis of where philosophical problems lie and where there are superfluous or does not arise follows. Certainly if there's a mathematical derivation which is satisfactory to everybody in business, even if there are small exceptions or absolutes and deltas, that's not something for specific philosophical concern. in this case, the big philosophically interesting question is, since the Boltzmann equation expresses irreversible behavior, since the underlying mechanics is known, where exactly was the assumption or group of assumptions that introduced that irreversibility, and what type of motivation did we have for making those assumptions? Now there are many mathematically quite sophisticated procedures for the technical question. This Swan-Seeker technology is one of them. Lanford theorem is another one. And there have been other people who have proposed a variety of mathematically extremely complicated techniques which are supposed to answer those questions. The philosophically interesting, or at least what I think is relevant questions, in some cases it's extremely hard to pinpoint. The answer to the question I just raised is, what assumptions in this approach are actually responsible for introducing irreversibility or breaking of time reversal invariance? And if not, sometimes the time reversal, the irreversibility is sort of illusionary, and maybe it results only because we restrict ourselves, artificially I would say, to consider merely positive times after the initial state. If we want to, the Boltzmann equation seems to be a reasonable description of the behavior of gases, even if we don't look at them, and even if we don't pick out one particular time as being zero, and it will hold for the entire stretch of time. Now, if we got a particular approach, we'll say, yeah, well, for positive time, we get the Boltzmann equation. But for the other half of the time region, we don't get it. Have we gotten back the Boltzmann equation? Or have we got irreversibility? No, I wouldn't say that. I would at least think that there is still some philosophical argument that has to be made in addition to that.
Can I, so I think I understood what you're getting at.
I don't take that as being disagreement with what I was going to say.
Yeah, I know, exactly. So let me try and just restate your question. You can tell me if I've got it wrong. We'd all like to believe that there's a result out there of the following form. For generic systems, in other words, for the sort of system that we normally run into, the H theorem obtains, and thereby we have a molecular grounding for ordinary thermodynamics. Now, the difficulty in what I've just said is that introductory clause for generic systems that we typically run into. We don't have a precise way of specifying that. If we did, then it would be a matter of proving a very hard theorem.
Say, yeah, that would be a way of saying
so the difficulty that we're facing is that statement is something that's only elusively glimpsed. And yeah,
yes.
Is that what you're getting at?
Yes, I mean, rephrasing that, the mere fact that there's some mathematical result that we don't know how to prove needn't necessarily be a conceptual obstacle to understanding, to thinking our situation is much less good than that.
But
yes,
it seems to me there are two issues here. One of which was just settled in a way that I agree with, but there is even if we're able to prove that say under generic initial conditions for generic systems, the Stosszahlansatz is true for a pretty long time, blah blah blah. There's still going to be what you're saying you're worried about, which is the choice of a zero time, the choice of a time, before which we don't expect it to hold. That, it seems to me, is going to amount to some kind of choice of initial condition. I mean, why you think, it seems like you think that wouldn't be a good way to talk about it. It wouldn't be a good way to address that problem. That I'm not clear on. That is, so here's where I take it things stand. The result that everybody, the mathematical result that everybody is saying they hope for, okay, is that under generic initial conditions, under some set of generic conditions, you've got reliable theorems that the entropy is gonna rise on average monotonically on both sides of those conditions, okay? On both temporal sides of those conditions, okay? Good. Everybody agrees that that's the theorem they're hoping for, that that's the theorem that sounds plausible, blah, blah, blah. You still seem to have, but then everybody else seems to be saying, okay, then we know what we need to do. We just set that point as the initial conditions of the world or something like that, and go on and throw out the part to the left of that. And you're saying you've got a problem with that.
Yes, well, clearly, that depends on the generic type of system. And what we're talking about here is classical mechanics. And apart from the time reversal invariance, there is another symmetry which is undoubtedly in play here, and that's time translation invariance. It shouldn't matter. There is no particular preferred instant of time in theory. So it shouldn't matter which time I take to be t equals 0.
Well, you're choosing different solutions by different such choices. That is, we don't expect particular solutions to have time translation invariance. We just expect...
No, of course not. But the theory is.
Yeah.
And we don't want to get theorems, general theorems, which don't respect that time translation. Solutions might.
Right.
But
okay,
theorems,
but
no.
I mean, maybe I don't know. Wayne should. Maybe we shouldn't go on with this now. I'm a little confused, but there'll be opportunity to discuss this in connection with what I say tomorrow.
But
too.
yes, I mean, but to come back maybe to what I'm having a hard time understanding what David's position is. But you made a good effort. So.
You mean this way?
With respect,
yeah.
I'm not sure whether David agrees with that, but in saying something that I can respond to.
I largely agree with what John said. Yeah.
Okay. I haven't spelled out in incompleteness what the philosophical issues or what the interesting issues are about this whole project. So yes, on the one hand, there is this problem. Boltzmann relied on the Stosszahlansatz. Can we actually expect that that result would be true, and we expect it to hold for all times? And there have been people working on that project. I am, as always, skeptical about how far they have gotten. But it's not to say that my skepticism is the only philosophical worry about the whole project. Certainly, there is a more constructive attitude that we might take on the whole approach. And that is also that we would like to know not only whether this is true for the hard sphere model, but whether it would be true for a generic type of system. So it's not like the discussion has to be at, oh, the Stosszahlansatz is valid, and other people saying, oh no, it's not. That kind of shouting is not going to help us. The constructive problem is, what are the type of systems, and what are the type of initial conditions for which something like this might be approximately true? Maybe for a finite time, or maybe up to some other nicety. And that's perfectly fine, because as I mentioned in the beginning, the whole idea that you could represent a gas by a distribution function, and that that distribution function is a continuous and differentiable function that might be put into an equation like this, that is a fiction and idealization to begin with. So the demand that anything like that should be literally true for all times is bound to get you into situations which might lead you to unrealistic demands. So that's not really the goal of the game. I agree completely. Why we are looking at those problems in foundations research, I think, is precisely because we want, if we know something about what motivates the Stosszahlansatz, we might also get a grip on which particular systems might actually be expected to obey something like it, and which systems we don't. And it's not like, oh, we're going to transpose this entire result to the beginning of the Big Bang is automatically going to solve our problems. Because at the very least, in the classical theory, in a model of the universe, we have to include gravitation. Now we know that the methods of kinetic theory and statistical mechanics and the thermodynamical limits are extremely hard. And, well, John Ehrman has written a survey article about the difficulties you get into when you try to talk about the entropy of the cosmos. And it's, at this point, to a large degree, just a pious hope that anything like this might be applicable to something like the entire universe.
In that position, I think John's article does rather overstate the amount of difficulty we've been had doing gravitational statistical mechanics. I mean, there is a wide field of that as a period of later.
Of course, but I don't think that all the problems have been satisfactorily solved. I mean, because
pious hope is quite strong, right?
Anyway, it's certainly not pious.
Pious hopes might come out.
Yes, can I just ask just a question notation? Someone told me that the H theorem is actually misnamed or misdescribed by the noises I just made.
Yes.
It might be capital Eta.
Yeah.
There's reason to believe it's a capital Eta. Yeah.
Yeah, there is there's a whole folklore literature. I mean, the first thing to say is that at the time, Boltzmann didn't have a name for the theorem. It has been common to call it the H theorem only since the 1890s. And nobody actually knew, of course, why Boltzmann wrote down a particular symbol on paper and what he had in mind. But yes, there have been speculations or maybe educated guesses to say that he had actually intended a capital Eta, and that would relate to entropy. Although the Greek writing of would use an epsilon instead. There's a similar recurrent debate in the literature about the missing factor n. And I think this, I mean, the term entropy was only very young. It had only been introduced by Clausius in 1863. And Clausius had all these various formulations of theorem. And at some point he would write things like for irreversible processes. He didn't actually have cyclic intervals, but never. And he didn't know about the inexactness of the differential. Sometimes he would write this, but he could also write this. And the distinction was just that in
Which
some,
way the heat's going?
yeah, which way the heat's going. Sometimes heat is taken to be positive if it's given off by the body. Sometimes heat is taken to be positive if it's absorbed by the body. And you can get things like that in different forms all over the place. Of course, this is just a conventional thing. But it's quite likely that Boltzmann got confused or didn't look at it so precisely, and therefore misinterpreted what he thought was entropy, with actually what we now think is minus entropy.
I think it's a good time to pause for that.
Yes.
Thank you.